everybody. Happy Friday. Welcome to Dome to Home. We're going to wait just a couple of minutes to make sure everybody can get online. If people need to refresh their browsers, give them just a second here. Hope everybody's having a great Friday. Looking forward to that Memorial Day weekend. Just a minute here.
Yeah, thanks for joining us this week, guys. We're excited. We're going to talk about some galaxies and the universe beyond today. Super excited for you on this lovely Friday afternoon.
All right, let's go ahead and get rolling here. Again, welcome everybody to Dome to Home. My name is Tara. I am a planetary scientist and a host here at Fiske, a presenter. Also have this guy here with me, Jeremy. Introduce yourself, Jeremy.
How's it going, everybody? Yeah, as Tara said, my name is Jeremy. I am a CU alumni, graduated about a year and a half, 2 years ago, and currently working at Fiske Planetarium, doing some outreach, presenting, and navigating. I've been working hard on making this Dome to Home show for you guys, and yeah, excited for the show we have today.
Yeah, Jeremy is awesome. He's going to be navigating for us today, which means all of the stuff that you see over here in our dome screen, he's doing all that live, all the flying around, putting up the pictures, putting up the dots. He's doing all of that. So super awesome. Now, just a note, the dome here on your, I guess it's my right, that's going to be best viewed in full screen. So once we get out into space, if you want to blow your screen up, it'll look really cool. And so right now we've got a lovely picture up of Farron Field here on the University of Colorado campus. And this is kind of what it looks like outside right now. That's what it looked like when I walked in earlier. But obviously we're not going to see too many stars or galaxies or anything like this. So we've got that one really big star in the sky that we need to get rid of. So Jeremy's going to fast forward through time for us so we can set the sun.
Yeah, let's go ahead and right now we're kind of looking a little bit zoomed in. Let's go ahead and imagine that we can lay on our backs and take a nice look up at the sky here.
Beautiful.
There we go. So we see the sun moving towards that western horizon over those beautiful flatirons in Boulder. Speed up time a little bit using the power of the virtual planetarium. And we'll get into the evening. Venus actually currently is really, really bright right on that western horizon right after the sun goes down. So encourage you guys to go out there and check out Venus.
If you're really lucky, right at sunset, you might also catch Mercury. You know, Mercury is always really close to the sun, so it's hard to see most of the time, but sometimes, especially right now, you can just barely see it right at sunset. So it's worth checking out. All right, so here's our beautiful nighttime sky here in Boulder, and this is maybe what it looks like kind of where you are. You can see some stars there. Maybe you can see a little bit of like a cloudy line going across there somewhere.
Yeah, maybe just barely.
Just barely. Yeah, so that is our Milky Way. If you've ever seen those kind of clouds, that line of clouds in the nighttime sky, maybe you haven't, because maybe your sky looks like this all the time. But if you were to go outside, way far from the cities, here maybe out into the mountains around like Netherland or even farther out, your sky looks a little bit more like this. Yeah.
That's a little better.
Yeah, I love that. Never gets old. So now you can really see our Milky Way galaxy. At least this is what it looks like from here on Earth. You can see the dark dust and the clouds and some of the bright stars. But since we're in a planetarium, we can get an even better view if we leave the Earth entirely. Is that cool with you guys?
Sounds good to me. Let's do it.
All right, take us out, Jeremy.
Get off that Farron Field view for you. There we go. Rising above the Earth. Gorgeous blue marble there.
Yep, our big, beautiful Earth. You can see the sun there in the background. So even from just off the Earth, you can see the Milky Way. It still has that kind of cloudy look to it. But we're going to pull even farther out. We're going to get away from the Earth so we can get a really good view of our galaxy. And while we're flying around and doing all this stuff, we do have our friend Emily here who's monitoring our chat here on the YouTube channel. So if you guys have any questions or anything you want to talk about, just throw it in the chat there and Emily will pass it on over to us. I'll try to answer some as we go, but we'll have time dedicated at the end for questions too.
All right, so this white line that we just brought up is the orbit of the moon, farthest that any human has ever traveled. And I want you guys to think about that. So far, that's right. When we're zooming all the way to the edge of the universe, think of just how small that distance truly is. Start speeding up a little bit. Right now we're moving much quicker than the speed of light, much quicker than any spacecraft that we've ever sent out.
We're nowhere near the speed of light just yet. So now you can see the orbits of all of the planets. The blue one is Earth, red one's Mars, of course, and then all of them going out from there. And our solar system is getting real small.
Bye, solar system.
You barely even see it now.
Start to see some of the stars moving.
Yeah.
Maybe orbit around here a little bit. See some of those stars moving further and further. Oh, we overshot it.
Too far.
Oh no. Flew a little bit got a little bit ahead of myself there. There we go.
So excited to show you guys the Milky Way.
I know.
Here we go.
That looks about right. So is this an image that we've taken of our own Milky Way, Tara?
This is not. We've actually never taken a picture of our Milky Way. We don't really know what it looks like because we've never been outside of it. We've never sent anything this far. We've barely come outside of our solar system. So we do the best that we can. I always tell, when I do this for little kids, I tell them it's like drawing a picture of your house if you've never been outside. How would you do that? You can walk around and see where there's walls and where there's open spaces. You can look out the windows and see what other houses look like. And that's basically what we do to put together a picture of our galaxy. We can see where there's really dense areas, where there's lots of stars, and more open areas where there's not as many. And we can look out at other galaxies and see what they look like and kind of piece it together like that. So this is kind of our best guess at what our Milky Way galaxy looks like. Now, our galaxy is what we call a spiral galaxy for pretty obvious reasons. It's got sort of this spirally shape to it. It has those big blue, what we call spiral arms. They're like arms kind of wrapping around the Milky Way there. And you'll see that they're very blue, but they've also got these kind of cloudy, dusty areas. You can see Jeremy just put up a note for where we are. We're out in one of those spiral galaxies, sort of out in the suburbs of our galaxy. Now, all of that dust and the blue stuff and the pink stuff that you see in those spiral arms, those are areas where new stars are being born. These are star formation areas that are happening here. If you were at our talk last week, you heard us talk about nebulas. So when an old star dies, it kind of explodes and shoots all this gas and dust out into the solar system or out into the universe. And all of that gas and dust is what condenses to form these new stars. We can show you some really awesome pictures of a couple of nebulas here.
Yeah, so this first one is going to be the Orion Nebula, which you can see actually with your naked eye in the constellation of Orion. It'll be just kind of right where I guess the sword of Orion is. That central star is actually this nebula. The next one we can bring up is the Carina Nebula. Nice little all sky of that. And let's see, did you want to take a look at the Crab Nebula as well?
Yeah, let's do the Crab.
Okay. Let me just
That's
find
always
it
our
for you.
go-to nebula here in the dome. The Crab Nebula is cool because it's left over from a supernova that happened that was actually observed here on Earth. Not by us, it was by the Chinese way, way back in, what was it, the 1500s, I want to say? It was a very, very long time ago, but they have it on record. And it was so big and so bright that it was visible in the sky for weeks during the daytime. So supernovas, even if they're really far away like this one, could be really, really exciting.
There it goes.
How cool is that? So all that dust and kind of stuff matter that you see spoofing out like that, that's all of the particles and the elements that were inside this star or around it when it blew up. So these are all of our star guts. They get shot out into space, but then they come back together and make baby stars.
Yeah, I always think it looks like the inside of a pumpkin. Like if you like carve it out, all that like slimy kind of guts, the guts of a pumpkin's the guts of the stars.
Very, yeah, very apt. I like that.
I think, just real quick, I think that one was detected in 1054.
1054. I remember it was a really long time ago.
Yeah.
It was on July 4th. I do remember that. Not like it mattered in 1054, but there you go. And so, yeah, that's what's going on in these spiral arms. That's why they're so full of dust and gas and things like that. There's a lot going on there. So that's where all of our star formation is happening and all of our new stars are being born. Now, there's two other areas to our galaxy. There's the spiral in the disk, but then there's also what we call the halo, which is everything kind of above and below the disk. There's lots of stars up there. They're a little harder to see because they're generally older. They're not as bright. They're going to be dimmer. But those are all kind of in a big circle around us. So that's our halo above and below. And then there's that really, really bright spot in the middle. That's what we call the bulge. All right. I'll give you a second to giggle. So this is the bulge at the center of our galaxy. And it sort of bulges out like that. And it's the same reason it's super, super bright, because there are a ton of stars right there in the center of the galaxy. And there are a ton of stars there because there's also a very large source of gravity in the center of our galaxy. That's right, it's a black hole. So we can show you what the center of our galaxy looks like. It's pretty hard to see sometimes because there's a lot of stars and dust and gas in the way. But we've got a couple of really cool pictures that we've had taken with some space telescopes.
Let's see here. What image were you looking for, Tara?
That
the galactic
was,
center?
Yeah.
Okay.
Galactic Center 2.
Oh, having some issues finding it here. Bear with me, folks. There we go.
Well, while you're looking, I see we have a question from Mr. McFarland who wants to know about the angle of the galaxy in the sky relative to the ecliptic of the solar system. Is there a relationship? Absolutely. Well, sort of. Because basically galaxies and solar systems form in sort of the same way. They all start out as like big clouds of gas and dust that get some gravity and start to spin. And so because the galaxy formed first, it's spinning and it's became that flat disk first, and then all of the planets in the solar system that we're in formed in that same flat disk. So that's kind of how it ended up being the same. It's all rotating in the same direction in that same flat plane. So it does look a little tilted in our sky because the Earth is a little bit tilted. We're not straight up and down with respect to the rest of the solar system. We're tilted just a little bit. So the galaxy does look tilted in our sky, but it's actually the same as the plane of the solar system. We're all sort of in that same flat disk. Excellent question. Yeah, so here's our really cool pictures of the center of the galaxy. The ones you see on the top were taken with X-rays. It's really good at seeing through gas and dust, so you can get really bright images of those stars in the center. The one on the bottom was infrared light. So that's kind of like heat vision. So you see really hot stuff So you can see stars, but you can also see really hot gases and plasmas and things that are there at the center. But of course, you don't see a black hole there, which really, it's really hard to see a black hole. That's why they're black holes. They don't emit any light or reflect any light for us to see. So how we detect black holes is by looking at all of the stuff that's around it. Because black holes have a ton of gravity, they're going to affect all of those stars that are around them. So this here shows you actual data of the movement of stars at the center of our galaxy. So where there's the star there in the center of that image, that's where the black hole is. There wouldn't actually be a star right there. You wouldn't see anything. But all the little dots moving around it are the stars. And so you can tell that there's obviously something there that's causing these stars to move around in that kind of swirling pattern. See if we can run through that again.
Yeah, bring it back up for you. There we go.
So see how these stars are moving around and they'll get kind of close and then swoosh by really fast. They're getting kind of slingshot around. There's something with a lot of gravity right there in the center. So that's the primary way that we find black holes now, is by looking at all the stuff around them and how they affect it, because they have a big effect on the things around them. So that's our Milky Way galaxy, our spiral galaxy with the black hole at the center. But we're not the only spiral galaxy. There are lots of spiral galaxies out there. We can show you some pictures of a couple of them. We've got a great little montage here. You see some of them we're looking at edge on, so you can really see that dusty, gassy bits. And of course, that one there at the bottom is not a galaxy. That is a scientist. Her name was Vera Rubin. She's kind of like the queen of spiral galaxies. She was the first person to realize that these spirals, when they're rotating, are moving so fast. They're rotating so fast that if only the gravity from their stars was holding them together, by rights, they should just fling apart. There's not enough gravity holding these things together for the rate that they're moving. And so that basically was like a catalyst for people to start thinking about dark matter. There's something else that we can't see that's holding all these galaxies together. So she was one of the pioneers of our understanding what we do know about dark matter. She was also a pioneer in a lot of other ways. Being a woman scientist in the 30s and 40s is not an easy thing to do. She got rejected from several PhD programs because they didn't think women could do this kind of science. She was not allowed to speak at a conference because she dared to be pregnant and try to do science at the same time. Heavens. She even had to build her own facilities so that she could work at the Palomar Observatory. She was literally kicking in doors for women in science. So we love Vera. Vera Rubin is awesome. Just had to plug that in there. But of course, there's more than just spiral galaxies too. There's other kinds of galaxies out there. So we have spirals like our Milky Way, but also even just in our local kind of galactic neighborhood, we have tons of other galaxies. There's some that are called elliptical galaxies. There's just sort of blobs of stars. They don't have a real spirally shape. They don't really have much shape to them at all. They're just a whole bunch of stars really close together. We can show you what some of those look like too. You can see there's our Milky Way still in the middle.
Oh, did you, you said ellipticals, right? Not irregulars? Oops.
Don't get ahead of yourself.
I'm just jumping way ahead of myself today.
It's just, I'm excited.
There's some elliptical galaxies.
Yeah, these are our elliptical galaxies. So you can see not a lot going on there, just globular. And elliptical galaxies are where we find the oldest stars in the universe. These are really, really old areas. You don't see a lot of those blue cloudy star forming regions like we have with the spirals. It's all very old, reddish, whitish stars, been around a long time. But As Jeremy just pointed out, we have our spiral galaxies, we have our elliptical galaxies, and then we have some that are sort of in between that are called irregular galaxies because we're really great at naming things. They're not quite spirals, they're not quite ellipticals, they're somewhere in between. So here's a couple of those. And you can see the one on the left, the bluish one, kind of looks like a spiral galaxy that you drove a truck through, maybe. That's kind of what happens. With these irregular galaxies, a lot of times they are the result of galaxy collisions or galaxy mergers. Because galaxies are moving. They're not just spinning around the black hole in the center. They're also moving through the universe. Everything in the universe is moving all of the time. And occasionally these galaxies will collide. Here's a really cool simulation. I love this thing. It's got simulated data, but then there's also interspersed pictures of galaxies in the process of merging. So these are actually galaxies that we have seen. So this is the simulation part. Swirl it around. But these are two galaxies that are actually in the process of colliding. Like, how cool is that? And so they'll run into each other. Sometimes it's sort of a glancing blow. Sometimes it's a head-on collision. And it'll just it kind of makes a mess. Probably what you would assume would happen when two galaxies collide. Everything goes everywhere. And so you can end up with big tails of gas and dust that are swirling around. All of this stuff running into each other can trigger a lot of star formation. You have a lot of really big things slamming into each other. And so that's going to be a lot of heat and pressure building up. And so new stars will be born. It's a really, really cool thing that happens. And not to scare you guys, but our galaxy is on a collision course itself with the Andromeda galaxy, our nearest galaxy, which is still 2.5 million light years away. Somebody correct me on that. I messed it up last week and I should remember it this week. But it's our closest neighboring galaxy.
Did you say Andromeda?
Andromeda.
Yeah, 2.5 million light years.
Million. Okay. Last week I said billion and I had to correct that too. So 2.5 million light years away. So it's still really far. And if it does end up colliding with us, it won't be for another like 5 billion years. So we got some time. We're probably not going to be around to see it, but it is a thing that is probably going to happen. So that's cool.
Right. And just to make a quick note, I am making these galaxies much, much bigger than they actually are in real life, just to make them a little bit easier to see.
Yeah, normally galaxies are very hard to see. There is a galaxy that you can see with the naked eye, and that's Andromeda. You can sometimes see it in the summer if it's really, 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 really dark where you are. Just like it's hard to see the Milky Way, this galaxy is very far away, so it's very difficult to see. And even when you do, it just kind of looks like a little fuzzy ball. But you can see another galaxy, and that's pretty sweet. But we're still just in our kind of local neighborhood here. These are some of the galaxies that are close by to us. Let's look at how many galaxies there are in the entire universe, because it's mind-blowing. Now, Jeremy's already put up some of these dots, those little green dots that you see. Those are not individual stars. Those are galaxies, entire galaxies full of billions of stars.
But there are more.
But wait, there's more. Here's even more galaxies. The different colors that you see here are different densities. So where you see the red clumps, that's where there's a whole bunch of galaxies pretty close together. The greens and the blues are where they're a lot farther apart. But we can keep going. We're not done yet. Look at all those galaxies.
Zoom in further and further away from our home. Start to finally see some of the large scale structure of our universe.
There is some structure to the universe. That was another thing that Vera Rubin was famous for, is helping us kind of identify what we call the cosmic web. It's sort of a spider web looking structure to our universe. There's huge lanes of gas and dust that move between galaxies and kind of link us all together. Super cool. So now we are way out at the edges of our known universe. And again, these are not individual stars, all these little dots. Those are whole galaxies. They're probably wondering why there's those black wedges in the center. Because we're human and because we're here on Earth, that's the short answer. This is what we have seen so far with our telescopes. It's not that there's not galaxies in those black areas, it's just that we haven't seen them. Now, the two big black wedges, that's where our galaxy sits. That's the plane of our Milky Way. And because there's all of those stars and gas and dust, like we talked about, it's really hard to see through all that. So it's hard for us to see any galaxies that are lying right in that same flat plane. We can see things above and below it, though. And so that's why we get this sort of wedge shape. You can also see that one wedge is about brighter than another wedge. That's the one on the top is the northern hemisphere. We just have a lot more telescopes. There's a lot more people looking. The southern hemisphere is a little harder to get to where their telescopes are, so they don't get quite as many observations. We're hoping that picks up pretty soon, though. They're building some new really cool telescopes down in Chile. That's going to be exciting. So there's probably just as many galaxies in those dark areas as there are everywhere else, which is crazy. So just think about all of those are galaxies with billions of stars. And we're pretty sure now that almost every star has at least one planet going around it. So that's billions of billions of billions of planets out there as well. So that's a pretty exciting thing to think about, I think. And on that note, we've just a little bit of time left. If we did have any questions that came through, check with our chat moderator. Or if anybody's thought of something real quick. Otherwise, we can just show you more cool galaxy pictures.
Is there anything beyond this, Tara?
Out at the very, very edges, there is what we call the cosmic microwave background. CMB is the easier way to remember it. And this is like kind of like a bubble of energy, of radio waves, or sorry, microwaves. That's as far as we can see, though. To see all the way out to this level, we have to use really, really sort of low energy, long wavelengths that can travel through gas and dust and things without getting interfered. But this is as far as we get. Once we get to this point, all of this energy out here at the edges blocks our transmissions, our radio waves, or microwaves. So we can't see through this. This is as far as it goes. As far as we know, that's as far as we can see. What's beyond that, if anything, we have no idea.
And it looks like Amanda was wondering what the colors were in the galaxies. So the colors, the blue and the red in this CMB are just tiny little fluctuations in temperature, just to show you like kind of just the differences. The colors in the galaxies, actually I'll zoom back in here for you. Those mark different like densities. So I think the redder colors are areas of space where there's more galaxies tightly packed in there. Let's see if I can zoom all the way back in here a little bit. Start seeing some of those colors show up. Yeah, there we go. So you can see on the right side of your screen, there's like a little grouping of yellow. That's like a more densely packed region of space.
Yeah, you can see some reddish ones there towards the top, some greens. Super cool.
Let's see, any other questions about space, the universe, galaxies?
Here's one. Tara, what do you think of the multiverse theory?
Ooh.
I think the multiverse theory is awesome. So if you're not familiar with it, that's the theory that our universe is just one of an uncountable number. Some people put a number on it. Some people say there's infinite numbers of universes. every time a quantum event happens, which is like every nanosecond or something like that, a new universe is created. This is a theory that it's very popular in quantum mechanics. I'm more familiar with it from the Michael Moorcock books. I don't know if you guys read the Elric series. Highly recommended. Those are fun. I think it's a really cool idea. We don't have a way to prove it yet, but it's really cool. There's a lot of people looking into it. I think if we did find multiple universes or parallel universes, that would be awesome. Excellent question.
That is a great question.
Let's see. All right, I don't want to mispronounce your name. Is it Tale? Tale? Sorry if I butchered it, but wants to know if there is water. There is tons of water in our universe, but there's a caveat to that. Liquid water is harder to find. Now, hydrogen is one of the primary elements that makes up our whole universe. It's lots and lots of hydrogen. And we know water is made up of hydrogen and oxygen. Oxygen is also made inside of stars. And so there's a lot of oxygen out there too. But it has to be just the right conditions for that hydrogen and oxygen to smush together and stick together to make water. Now, in our solar system, there's a lot of water. We have water here on Earth. There's a lot of moons that have water on them, one around Jupiter, one around Saturn, maybe some of the ones around Uranus and Neptune. We're not really sure yet. But even if there's not liquid water, there's ice, tons and tons of ice out in our solar system, probably in other solar systems. We found planets around other stars that have water in their atmosphere and clouds just like we have. So water is actually pretty common out there, which is exciting because it's one of those things that we look for when we're talking about life elsewhere in the universe too. So if there's water, there could be life, and that's pretty sweet. So you also wanted to know what holds galaxies together. Another excellent question. Basically, gravity. Gravity is what holds everything together. It keeps everything mushed together. But galaxies, like Vera Rubin found, don't really have enough stuff to hold themselves together. So most galaxies, almost all of them, we think, have that big, super massive black hole in the center that has tons of gravity. And so that holds a lot of it together. And then all of the stars in the galaxy have gravity too. And so they kind of keep things close into each other. But there has to be something else out there. And that's where the idea of dark matter came from. There's something out there that has gravity, but we can't see it. So this dark matter is out there, and that's what's keeping a lot of the galaxy together. There's a lot of dark matter out there. We're pretty sure. There has to be. We haven't seen it yet. We haven't found it. But basically, gravity from the black holes and the other stars and all of this dark matter is all kind of keeping the galaxy held together like that. Good question. Everett wants to know, how can we detect the edges of the universe if it's billions of light years away? That is true. It's about 14 billion light years. That means it took about 14 billion years for the light in these objects at the far end of the universe to get to us here on Earth. Now, it doesn't mean that Earth has been around that long. It just means that the light has traveled that long. So that's as far as we can see is stuff that started 14 billion years ago. That's why we kind of put our age of the universe at that point. Because we know how long it takes light to travel, we can kind of get an idea of how far things are away based on, we have certain standards of brightness. Some of things in the universe are really only exist at a certain brightness. So by judging how bright they are in our sky or with our telescopes, we can get an idea of how far they are away. And so we use these sort of techniques to figure out how long light has traveled to reach us. Let's see. Question from Hubert about how do we know if ice is made of water and not frozen gases? Excellent question. That is my jam. Ices are awesome. The way that we tell them apart, especially if we can't get to it, like things on faraway planets that we haven't landed on, or exoplanets that we can't get to, we use a technique called spectroscopy. And it's basically, we shoot light at it, and that light bounces back to us. Now, different elements, because they're made up of different stuff, they have different shapes and different molecules fit together. They'll reflect that light back differently. So if we shine a light on something, we look at the light that comes back to us and we can see how it's reflected and where there's more light bouncing back, where there's less light, and use this to tell what sort of elements the ice is made out of. So we can see if it's water ice or if it's nitrogen ice like they have on Pluto. Carbon dioxide ice is really popular on Mars. Really cool stuff like that. So yeah, spectroscopy is a lot of what I do, especially with ices. It's really, really fun. It's one of the most useful techniques that we have in astronomy because we can do a lot of studies with stuff that we can't get to, which is, you know, most of the universe we can't get to. So this is kind of how we decipher what things are made out of that are really, really far away. Great question. Let's see, Mr. McFarland again. Is there a more accurate term for a galaxy that isn't the derivative of the same name as Milky Way? So, trying to think of, Milky Way is really just the name that we gave to our galaxy, and I don't really think it has any other specific designation per se. The way that we name galaxies, a lot of times they'll be named based on the constellation that we see them in, or a lot of times based on other, you know, star systems that we have seen there. So they'll have names like M87 or NGC674 or something like that. As far as I know, correct me if I'm wrong, Jeremy, but I think our galaxy is just the Milky Way galaxy.
Yeah, I think you're right on that.
I don't know that it has any other more specific name. Really, naming things is just something we do as humans. So any name that we gave to it wouldn't mean anything to somebody from another star system. They may have a whole other name for our galaxy or our star or our solar system. So naming things is a very human thing that we like to do, but doesn't really have any real significance outside of how we feel about it. Good question. I like these ones, you make me think a little bit. Anybody else? If not, we can go ahead and call it a day. But thank you guys so much for joining us today. We've got another one Dome to Home session coming up next week. We're going to talk all about black holes. It's going to be super cool. Now, because Monday is a holiday, if you're planning on joining us for the K through 5th grade show, that's going to be moved to Tuesday. So that'll be Tuesday at 11 for K through 5th. 6th through 12th grade is still going to be Wednesday at 11 Mountain Time. And then we'll have our public show at 4 o'clock on Friday as usual. And good news, Dome to Home has now been extended through the summer. We were going to end it up with black holes, but now we're just going to keep on going. So we're only going to be doing one show a week. It's going to be Tuesdays. June 2nd will be the first one. Not sure on the time yet, but we'll let you know as soon as we know. Hopefully, if you check in next week, we'll know by then for sure. Or just keep watching our YouTube page. Check us out on Facebook and Instagram and Twitter. We're all over the social medias. If you did have any questions that you couldn't think of right this second, or you want to check in with us later, go ahead and leave us some comments here on our YouTube page. Like us, comments, all that good stuff. Otherwise, I think we're set. So for me and Jeremy and Emily, thanks you guys for coming out, and we will see you next week.
Thanks, everybody.